Welcome back. Welcome back to our third E2 video. Let's mark a number round 3. Okay, we left off with a nice example of a tertiary electrophile, and I kind of feel a table coming on. Okay, so here's where I would start. I would take a look at the electrophile, and I would figure out, okay, first of all, where's your leaving group? Let's see if we can write a nice substrate like this. Let's go like this. Okay, so if your leaving group is here, that means you have a nice primary. Okay, primary means that you're going to undergo an SN2. And that means an SN2, you're not competing. You are going to have an SN2 with anything on your list. Okay, so your list as is, SN2. Okay, now here's where it gets dicey. What if your leaving group is here? Well, now you have a secondary. Now you have competition. Now it's an SN2 versus an E2, and you've got nucleophiles on your list or electrophiles, bases. Electrophiles, E is for elimination, not electrophile. So this is where you've got to check your list. Which one do you have? And then finally, what if your leaving group is here and you are now tertiary in your electrophile? Well, now you're actually just to E2. SN2 isn't going to happen there. So if you have a base, now you've got an E2. So really, this is pretty awesome because, I'm going to say base only, because your SN2 list of nucleophiles, that reaction just isn't going to happen. So really, you have to be careful on the secondary. That's where you're going to have that competition. Okay, now if you're thinking, Dr. Morty, please challenge me. It's not that, I'm sorry, that just made my daughter laugh. We're not quite done with the story on our E2. So let's have some fun and let's do a little bit of a review. Okay, I'm just going to include, remember, we've got our lists right here. So here's your two lists. Here is your list that's going to act as a nucleophile. Here's your list that's going to act as a base. Now we need to grow this list. Let's get a little bit modern. So let's take some more examples of an E2. And if you're thinking, wait a second, there are 4 components to each one of these reactions, and we only talked about 3. You're exactly right. We need to add some more details. So let's take something as nice as bromobutane, and let's get a little bit deeper with our E2. Okay, so let's mix it with a base, and I'll go ahead just for funsies and keep this one as sodium hydroxide since we've already been using that. And let's see if we can predict what we're going to make. Okay, now watch this. I'm going to add a solvent. Shut the front door. I just used water as our solvent. It could be all kinds of things, but we typically match our base and our solvent. And I'm going to come right back to that when we draw our products and tell you what I mean by matching. But all the way through OChem 2, when we have those O minuses, we tend to match base and solvent. Okay, so what's the first thing we've already been trained to do? Find your leaving group. Holy cow, this is a secondary electrophile then. Your electrophile is secondary. So we check our list. Check your list, and it turns out that our OH is going to act as a base. So this is our signal. Aha, this will be an E2 reaction. Done. So now we've got solvent, base, electrophile, and leaving group. So what are we trained to do next? If you can have an E2 reaction, you have to have beta hydrogens. So this is where the plot thickens. I love it. And if you're a sassy organic professor, this is where you start to monkey with your students. Of course, you don't tell them ahead of time. That's what makes me nice. So I am going to monkey with you here, but I'm also telling you ahead of time. Look at our beta hydrogens. Right here is our alpha. So that means beta next door. So let's just go ahead and draw a hydrogen here and a hydrogen here. Shut the front door. We now do not have symmetry. These beta hydrogens are different. What? The plot thickens. I love it. So here's what I want to do with this example. I want to go ahead and draw all three possible products first. Then we're going to slim it down. So I'm telling you right now, there's actually three possible products, but what? There's only two beta hydrogens. I know, this is where it gets so fun. So let's draw them. Okay, let's start first with this beta hydrogen. Let's start here first. So I'm going to go ahead and draw the mechanism, and we're going to look at all of them. So I'm going to include this beta hydrogen, okay? And I'm going to take that OH minus. And where do we go? It's going to act as a base, so you're reacting with hydrogen, that proton right there, okay? These electrons collapse, that's what makes your double bond, and you lose your leaving group. Okay, I love it. Done. So where does your double bond end up? It always ends up between that beta hydrogen and that leaving group. That's what you eliminate. So you just made that alkene. I love it. That's product number one. Okay, now here's where the plot really thickens. Let's take the other one. Our mechanism is virtually the same. It's all about a competition of collisions. So what is your base going to bump into? Well, it's going to bump into that beta hydrogen. And now we have, which way do we go to collapse those electrons? Has to go towards your leaving group. So then now, let's check it out. We can make this alkene. Okay, or shut the front door, check it out. This is where we stop and pause for a minute. Alkenes, if you've got a model set, this is a great opportunity. Do you remember when we modeled cyclopropane in our first unit? What happened? Could our bonds rotate? No. Once you form a double bond, this bond does not rotate. You are now fixed in space. So, you know, this is why this is so exciting. What happens when you fix that bond rotation in space is that you get possible configurational isomers. This is where we first saw cis and trans. Our alkenes have a version of cis and trans as well. So check it out. This one has hydrogens opposite. This one has them on the same side. So this is trans. This is cis. These are configurational isomers. Both are possible. So this is why I said we get three possible products, and then we're going to slim it down. So we can have that outside alkene, or we could have that more inside alkene, and we could have a cis or a trans with that inside alkene. Now let's be very careful. When we're looking at cis and trans on an alkene, this only works if you've got two hydrogens. As we get sassier in our examples, we have to use a different naming system for that. That would be E and Z. So even if you're used to hearing cis and trans, we won't be able to use it for everything. They have to have those two hydrogens there. Okay, let's start to compare. The first thing I'm going to add to this is a little equilibrium arrow. When you use a base like sodium hydroxide in its conjugate acid, what are our other products here. Remember, what else do we make from these? We make water and salt. Oh, BR. So this is what we mean by matching. The conjugate acid to your base is the matching solvent. Okay, this is setting us up for a nice mini equilibrium reaction. We talked about this in our acid-base chemistry, that we can have a nice equilibrium reaction. And if we look at pKa's, we would be evaluating the pKa of that conjugate acid, which is water. That pKa was about 16. Okay. So this reaction, because it's possible to be in a little bit of an equilibrium, we are going to call this something called thermodynamic control. Anytime your reaction can go backwards and forwards, anytime it can be in equilibrium, you will always make the most stable product. Because Mother Nature is letting you go back and forth, you'll always end up with the most stable product. So out of all three of these, let's figure out which one is the most stable. Let's start with the easy one that I know that you can predict. Between cis and trans, we've seen that before. What does your gut tell you energy-wise? Which one is more stable for our double bond? Would it be the trans, where everything is nice and spread out, big hint, or the cis, where you're actually forcing these methyls close in space? You are totally right. This is actually your most stable, would be the trans. So let's go ahead and put an X through here. In these reactions, in fact, you don't see the cis unless you have no other option. So in fact, our most stable is that trans isomer. So now let's compare these two. How do you compare the energy on those? They're kind of similar. The only thing that's different is how much stuff is around your double bond. It turns out that the more stuff around your double bond, so the most substituted alkene, will be more stable. This is something called Zetsef's rule, if you're reading in a textbook, that the more substituted, the more stable. So if you've got something like this versus this, then we are going to cancel out this one. This will be our most stable. So let's go ahead and cancel out this one and cancel out that bottom one. So from a reaction like this, we will end up making that middle compound right here. We are going to make the trans most substituted alkene. Okay, I love it. So let's just write that pretty for a second so we can write that in your notes. So if I really were to take bromobutane and treat it with something like sodium hydroxide, what we're going to really end up making as our major product is the trans most substituted. Perfect. I feel a color code coming on. Okay. And then, of course, we'll have water and salt. Okay, write that down. That's perfect. Now, what if in your heart of hearts you really didn't want to make that one? What if that has so been done, right? Oh my gosh, that's been done. What you really want is this one. What could we change in order to make that one? Okay, we don't actually need the solvents again. Okay, that's a cliffhanger. So that will be our next